Hi, my name is Angela Nguyen, and today I'll be presenting on Lab 2. So the purpose of this lab was to observe an object falling from rest and assess how two computational models would reflect the observed motion, one which takes into account both gravitational and drag forces, and the other just the gravitational force. So the result of this experiment showed that the model that accounted for both the drag and the gravitational forces was more accurate in representing the observed motion than the one accounting for only gravitational force. In this experiment, we have an object that's falling from rest, so it has zero velocity. But as it falls, we see that the velocity increases. Through Newton's second law, because of the change in velocity, there is an acceleration in net force. We see it through this formula. And the acceleration of the net force by an object initially at rest is due to gravitational force, which is the attraction between two objects in the universe. And this is the formula for gravitational force, where it equals the mass of an object times the gravitational constant. Another relevant force is drag force, also known as air resistance, and it acts in the opposite direction of an object's velocity, and its magnitude is proportional to the square of the object's speed times some constant, some proportionality constant, which is b. So here I dropped a coiled hair tie, which represents the system, and the surroundings is everything else. I extracted the initial position from tracker, and the initial velocity would be 0 because the object is initially at rest. I used a light switch to calibrate measurements, and I manually tracked the hair tie as it fell over time. So for the first model, we do not take into account drag, only gravitational force. So I first updated the ball's initial position and velocity using the values from the previous slide. I also changed ball.vel and ball.pause in the while loop to reflect the update position and update velocity formulas shown here. And also, Fnet is equal to W here, which is equal to the mass times the gravitational constant from the formula I showed previously. And this is the model that we see. Moving on, for the glow script model that does take into account drag, I kept everything the same, except I added FD, or the drag force, and basically I used trial and error to find B, where the final position from the computational model was closest to the observed final position. And FD just represents the drag force here, the formula. I then plotted all three onto the same graph, and here we see that the computational model that did take into account drag and gravitational forces closely resembles the observed motion. Drag force acts in the opposite direction of velocity, and it slows down an object. But since the computational model without drag did not take into account drag, there is a greater decrease in the position in the velocity. So the final position for the no drag model is more negative than the one that did take into account drag and the observed. However, there are still some slight discrepancies between the observed and the computational model that took into account drag, especially towards the end here. And one of the reasons is possibly due to the coiled hair tie being subject to more drag, where the air was blowing it around more, so it was difficult to accurately track the hair tie's exact motion with tracker. So the model with drag and gravitational forces predicts terminal velocity. Terminal velocity is when the velocity increases, thus increasing drag until the drag is equal to the gravitational force, producing a net force of 0. Looking at these velocity graphs, the only one that took into account the gravitational and drag forces, do we see that the velocity does not change, it is constant. Whereas here we see that velocity does change linearly. So if we set the initial velocity to 0, -1, 0 to represent an object being thrown downward, we will actually still observe the same terminal velocity as when velocity was just 0. as when the initial velocity was just 0. And this is because terminal velocity does not depend on initial velocity, but rather on the object's mass. So it makes sense that terminal velocity is still the same. Thank you.